the entire workshop, and I will aim to get that edited and put online so you can all pick it up and watch it at your own pleasure after we've finished. So you can go through it slowly and pick up on what we've been doing. Right. I've got some data prepared for this, so I'll just bring up that so we can have a quick look at the data set that we're going to work with. Right. So we have a variety of different data sets in here that we're going to be importing throughout this workshop. So we're going to start off with some elevation data from LAS files. So that's LiDAR data. Then some satellite imagery, the OBJ files, which are the digital outcrop models. And then if we've got time, we'll bring in some other things like billboards and look at how they can be used. I did send a message out to say if anybody has got questions, I will be happy to answer them. I've had a couple of questions through. Okay, somebody's to everyone, yes, a couple of questions already. Can you just all make sure you've got your microphones muted? Make sure that we're not getting any feedback. So thank you very much. And hello to everybody who said hello in the chat already. Right. So if you've got questions, just put them in the chat and I will endeavour to answer them. I had a couple of questions come through email, one of which we will cover anyway, but somebody asked about to know a bit more about structural mapping and fracture analysis. We'll cover a little bit of that, but that's also going to be the focus of the next workshop, which will be aimed at structural geology and fracture mapping. So might want to keep an eye out for that one as well.
لا بعدين صرت معك بروح ما تو بعدين.
Could we just all make sure we're muted, please? Still getting a few stray things coming through. Anyway, let's get on with it. Right. So I've started VRGS. And the first thing we need to do is we're going to create a new project. And I'm just going to call mine, very unimaginatively, Workshop 3. Because I've already got 2 other projects with similar names. So anyway, we've set that up. And we're going to start by setting our coordinate system. You don't always need to set a coordinate system in your project, but it can be very useful, particularly if you want to do coordinate transforms. If you look on the right-hand side of the screen, we have our project properties. This is the properties panel, and we can get to our project properties through this button here. And within that, we have EPSG codes. So EPSG codes are a set of codes that are defined for lots of different coordinate systems. If you just Google EPSG codes, you can find websites that tell you about all the different codes that there are. To set our code, you click on the button here with the 3 dots, and then we get our coordinate system definition dialog come up. If you know roughly what your coordinate system is, you can use the search. So for example, if I know I'm in a UTM zone, if I want to work with UTM, I can just start with UTM. And then I can see how the different zones are labeled. And I might want to then say, well, I know I'm in UTM zone 30. And then we see we've got north and south zone. So I could take that a little bit further. UTM zone 30 north. And I would probably want WGS 84 is a fairly sort of typical one. However, for this project, I happen to know that my EPSG code for this is 27700, which is the Ordnance Survey National Grid. If I didn't know that, I could just do OSGB. Ordnance Survey of Great Britain, and it would list the different codes that we've got, and there's 27700. So I'll select that one, and it appears in the coordinate properties here. Okay. That's set the coordinate system. We're ready to go. We'll start off by bringing in some elevation data. Here's a set of LAS files. These are 1 meter data spacing elevation data for the UK. It's from an area in the northeast of England called Whitby. It's a well-known exposure of Jurassic rocks. Lots of people do field trips there. This is public domain data from the UK's Environment Agency. All I need to do to import these is I've just selected them and I'll just drag and drop them into the 3D view. Quite a lot of the data types that we deal with, we can just do with drag and drop very easily to work that way. This has come in. So here's the first sort of problem that you might encounter with working with this kind of data, that it just comes out as we can see that there's data there, but there's no color to it. It's all the points are black. That's because these LAS files didn't have any color information associated with them. So we need to define some color information. We can do it very easily. By default, it opens up the subfolders for the point clouds, but just close them down. And we can select them all with holding down the Shift key to select multiple. Then I do in here, it is false color elevation. We don't have to bother about an offset. And now we have our elevation data set colored with a false color. So we can see the difference in there. If I hadn't have selected all of them, it would have scaled the color to the range of the single tile. But because I selected all of them, it scaled the color range to the vertical limits of all of the tiles together. Right? So we get a nice even color scale across the different tile boundaries. The area that we're interested in is here. This is where our digital outcrop model is going to be, just in this little locality. Give you a bit of geological context. During the Jurassic, when these outcrops were deposited, there is an active fault running more or less along the path of where this estuary is. And the rocks that we're going to be looking at are on the downthrown side. And because this fault was active during the time of deposition, the model is that the topography trapped a river system on this side of the fault. So we're looking at a multi-story channel complex on this side of a fault that was effectively going down the center here. That just gives you a little bit of a feel for what we're going to be looking at. Our next thing to bring in is we're going to bring in a satellite image. Now, I don't actually have any proper satellite imagery that I can use for this, but we can do something similar, is bring in some map data. So I know that our field area lies in this map tile. You can see this is all of the map tiles, set of map tiles that make up the whole of the UK. These are again available free of charge from the Ordnance Survey. Okay, so that's going to come in. Hey, we've still got some people with that haven't muted their microphones, and we can hear conversations going on. Tina, Can you mute the microphone, please? Thank you. Right, let's get back to it. Now we can see we have our GeoTIFF imported into the project, and it's correctly georeferenced, so that's come in the correct place. When we've got data like this and we've got our coordinate system set, there's a couple of things that we can do to first of all check that our coordinate system is right. If I go to the web view here and select the web browser, whoops, that's the wrong one. Go to my web view, and on, say, one of my point clouds, if I just do a go to, in the web view, it brings us to more or less the right place in Google Earth. So it's coming to the center of this tile here, which brings us to, you can see here, there's the harbor and the harbor there. So we've got this link between what we see in the model and we can bring it up in Google Earth. So that's quite nice if you want to look at Google Earth imagery alongside the model that you're working on, but it's a good way of checking that your data is correctly georeferenced. Another thing that we can do once we've got our georeferencing in place, and once we've got a model area defined, so there's our model area, you can go to the triangular meshes here and do download elevation. So this will pick up the global elevation data set or one of the global elevation data sets that's available through name of the website escapes me at the moment. I'll remember it in a moment, but we're able to open topography. They have a set of global elevation models that are available to download. I'm just going to here pull out the SRTM 90 meter, purely because we can bring in the higher resolution one, but for the purpose of this workshop, I'll bring the lower resolution one because they're quite big models and they take a while to download. But let's bring that. And we just have to wait a few seconds for it to bring the data down, and it will create a mesh for us. The thing that we've got some information coming up in the messages tab here that's telling us that it's doing the transforms. Always keep an eye on what's going on in the messages panel down here. Gives you a lot of extra information about what is happening. And here we have our elevation data set. And I can hear my computer whirring away. What you might find is when you bring in very big data sets like this, is that they can initially seem to be quite slow, but a trick to help speed it up is switch off your bounding boxes. And if they've got your bounding boxes switched off, then you find that your model will move much, much quicker. And there we can see the elevation data sitting in the same position as our image. Now, this image and the elevation data are now separate. We can apply that image as texture map from a right click on the mesh, find texture map. It will give you a list here of your available texture maps, and then we just select that. You may well find that when we do this, you need to do a refresh on that model. And there we have our elevation data with the texture map attached to it. So that's how you would deal with using satellite imagery and integrating it with your elevation data. Right, Our next step is to go and bring in our OBJ file. So this is our digital outcrop data set, and it's in here. I've got a model here that's got 7, 8 images associated with it, 8 textures, and your OBJ file, that's our preferred format. You can use PLY and some other formats as well, such as GLTF and GLB. But OBJ is the one that most people choose to use. And you should have your OBJ file, an associated sidecar file, as it's called, the MTL file, which is your material file, which explains which textures are being used, and then you have your texture images as well. They all need to be in the same folder, but you only need to drop the OBJ file into VRGS. It will know where to look for the material file and the textures just from the OBJ file. And it's starting the import process now. Depending on the size of your OBJ file, the importing can take quite a long time. You see here, it's going through each of the materials, each of those textures, and importing the triangles associated with each of those. It then has to do a little bit of extra processing to ensure that we can do quick visualization, manipulation, and interpretation of the data. So it does some internal restructuring, which is why you quite often get a little bit of a delay when you're loading data sets. But that only happens the first time you load them. Once you've loaded it once, then the next time you reload the data, it will be much quicker. Okay, so our data set is loaded. I'm going to switch off the large scale elevation data, and we've got no model. And that is because I'm going to do a go to on here. And we'll have a little bit of another wait now, because it will rebuild the textures that are needed to visualize the data. Oh, and I also need to switch it on. You can hear my computer is whirring away in the background here. And we're going through this building textures phase. This will only happen once, the first time you visualize it. Once you've saved it, it doesn't have to do this again. And there we go. Now I've done that, I'll point out that in your data tab, you have some information about the different objects defined by these color blocks. If it's green, it means everything is saved and is all right. If it's yellow like this, it means that something has changed with that object and it hasn't been saved yet. If it's red, it means there's something wrong with it. I'm just going to do a quick save. See, it's writing the point clouds and the meshes and the database, and now everything is turned green. So that means they're saved and don't need to do anything else for the moment. There's a problem here. If I go back to, say, one of my point clouds, our OBJ file, our outcrop model, isn't in the correct place. We need to georeference it. When you bring stuff out of your photogrammetric software, you'll find it will be internally consistent in terms of ratios, But quite often, unless you've done the georeferencing inside your photogrammetric software, the model will be in the wrong orientation and quite often the wrong scale. We need to fix that. We're going to do that by importing some waypoints to start with. I've got those in my data folder here. And there's as a simple text file. If you look on the documents site for VRGS, there is a section that shows you what the waypoint format is. There's several different formats you can use, but this one is basically, let's do. So as you can see, the format is simply X, Y, Z, and comma delimited. Over on the documents site, we have a description of the waypoints, and down at the bottom of the page, it gives you an overview of the different ways that you can format your waypoints. So you can use space or comma delimited, or add the name of a waypoint as an extra column at the end. Don't know what's happening with Notepad. It's not letting me do that. Anyway, it's a simple XYZ format, which is space delimited. So it's pretty straightforward. Right. We're going to go and bring that in. So waypoints, import, ASCII text. It's in my Northeast England folder. It's in here. Open it. It comes in and we find we've now got our waypoints imported. I can do a go to on one of these and it will take me to where the waypoint is. And these are tie points that I have taken GPS positions for in the field, one way or another, to tie our data to. A useful thing to know is when you're displaying things in VRGS, is you quite often get things like this, where you zoom in and you can see your waypoint nicely, and you zoom out and it becomes too small to see, and you want to be able to see where the others are. We can change the size of the objects. Most of these objects that we have, or groups that we have, there are group properties and individual properties. And for a lot of the features, so waypoints and labels and samples and things like that, you can change the display size. So we could just make the display size bigger and make them 10 meters. So now we can see our object. But of course, when you zoom in and zoom out, they become too big. There is another option here. Now, if I go back to what we had before, 0.5, there's another option here, which is maintain size. When you switch maintain size on, this display size goes from being in meters to being in pixels. And that's something that does confuse people. But now if we change that to say 10 pixels, as we zoom in and out, the waypoints always stay the same size on the screen. So let me make them even bigger. So they always scale to the same size, which makes it easier when you're working with quite large scale data to be able to find out where things are. Anyway, I'm going to take those back down to 1 and have them in meters. If we go to our ungeoreferenced mesh, you can see we're looking from above here. There's the north arrow. We're looking down, and obviously that's in completely the wrong orientation. There's a few places on here where I've got the waypoints. To do our georeferencing, we right-click and we select Make Active. And when we do Make Active on quite a few of the objects, not every object has a Make Active, you will get an extended menu system that's dedicated to this object only. So whatever's going on in this menu here, the triangulated mesh menu, is only applicable to the mesh that is active. It doesn't affect any of the other meshes unless you make those active, and it will deactivate the current one if you do that. Anyway, we're going to add in ground control point GCP. And we've got one that's there. And I know that that is of these waypoints is the first one. If I open up my mesh group for that particular mesh, you can see your tie points in here. These are the waypoints we've imported. I can right click and copy its position. So this is taking the position of the waypoint and set that to be paste as the target position. And now I've done that, we'll see in the tie point properties, we have the position of the tie points, its current position, and where it's supposed to be. And those are in OSGB, Ordnance Survey of Great Britain coordinates. And we also have a vector which is going off to where the correct position is. Now we'll do that for the next point, which I know is over here somewhere. And I used one of these rock bolts. This is a bit unstable, this cliff face, so you have these big bolts that have been put through to help stabilize it. So let's do another GCP, another ground control point, put it in place. And then we have a number 2, again, copy position, paste, target position. And then finally, we have our last target point. To actually georeference a data set correctly, you need at least 3 control points. And I know my last one is here. So do copy position and then paste target. And there are 3 control points are in, and our error vectors heading off to our actual real data over here. From the panel up here, here's the correction. So this is correct from ground control point. I'll just click that. And I can hear my computer whirring away now. And it's disappeared. I should then be able to do a go to. And there is our outcrop model moved into the correct position. But there's a problem. If we look at our control points and the error vectors, the error vectors are still quite large. There's still quite a big difference between where the control points are and where they're supposed to be. And we can see by the way that these vectors are that it's because the model isn't scaled correctly. If we're confident our control points are correct, we can just do a rescale here from control points. And again, we get a little bit of processing being done. And now you can see that the error vectors are all more or less the same length. So we just need to do a recorrect from control points again. Give it a moment or two to do the correction. And you see it's corrected the scale and put the model in the correct place. And now we've got a good tie between our digital outcrop model and the elevation data. So everything's correctly georeferenced. At this point, good time to save. Make sure that our meshes are showing green, and we can go on to the next stage. So the next process that I usually do is if we're working with a combination of your digital outcrop model and elevation data, you quite often want to make a good merge between the two. And at the moment, we've got a point cloud data set and a triangulated mesh And there's also an overlap between the two. You might just be able to see there's elevation data set points in our outcrop model. And we want to kind of get rid of those and then create a mesh. So there's a little process that we can do to make the tie between the outcrop data set and the elevation data set a bit better. We start off by going to our outcrop model, and in operations, we're going to do extract free edge polylines. And this will take a moment or two to run. What it's going to do is work out what the outside edge of the model is and create a polyline that maps just around the outside of the outcrop data set. It will also do round any holes that are in there as well. You will sometimes find when you do this, you get multiple polylines being generated. And it's still running. So it can take a little bit of time to generate because they're quite big models. There we go. And it's finished. Now it's a good time to introduce a concept in VRGS, is that we try and keep our data and our interpretation separate. That's why we have a data tab and interpretations tab. We also have collections. Collections are things that you can't visualize directly. It'll be like fasces descriptions or grain size classes. They're in a separate tab, but interpretations are found in here, and the polylines will go into the interpretations tab. We found now that it's generated 2 separate polylines. This is the number of vertices that there are in each polyline. So this is obviously the big one. And when I select that, you can see it's a polyline that tracks all the way around the outside edge of the mesh. So we're going to use that to help us merge the data. The next thing we do is we're going to go to the same data set. And in operations, we're going to do an extract free edge points, which is just going to pull out the vertices around the edge, but not join them together. And it will put that into point clouds. And again, we have to wait a moment. It's usually quicker when you do it to extract as free edge points, because it doesn't have to work out how they're all joined together. There we go. So what we'll do is we'll switch off the other tiles. So we only have the tile that we're interested in. For the moment, I'm going to switch off the outcrop model so that we can just see our elevation data and the outline. And I will do in my elevation data set here, right click, operations, and select inside visible polylines. And now it's pulled out where it can work it out, where the selected the vertices that are inside that polyline. I can then in here do, it's in operations, delete selected points, which gets rid of those. There are some other tools if we want to try and tidy this up a little bit more in edit. So we've got some selection tools in here. Now what I'm actually going to do is I am going to make a slightly larger selection. around the outside of the model. And you'll see why I'm doing that as we go on. So it's selected those. I'm going to do the same thing and delete the selected points. The reason why I'm doing this is that because you have this change in the resolution between the different data sets, your outcrop model is very high resolution and your elevation data is quite low resolution. You get round the edges of the model, you get areas where the data sets just don't match up very well at all. So we're going to clean those out. I'll do the same thing over here. Select around the outcrop data set. And then we do a delete. Next step is to generate a mesh from this. And we don't want to generate a mesh for everything. You might do when you're actually working on your data for real, but here we're just going to create a mesh for a small section, so it doesn't take very long. And to do that, we'll do select a rectangle on the mesh, and then we right click. Actually, there is something I've forgotten to do here. I need to take our elevation data and our free edge points, and we need to do a save on what we've done so far. And we need to do a merge on them to create a combined data set. So that data set has, when I switch my interpretations off, both the polyline data that we extracted from the outcrop model and the elevation data, which I can then, from this merged version, go to operations, triangulate. Sorry. So I said I needed to do the select, because otherwise the triangulation process can take a long time. So we're only going to triangulate this bit. Operations. Whoops, managed to deselect it. There you go. Operations, triangulate, and we want to set our maximum edge length to be something quite big. And everything else is just the defaults. We don't need to worry about anything else. Let's press OK. And now we have a version of our elevation data set that has both the outcrop edge points and the elevation data, but we've still got these big triangles in here. We'll go into interpretations, switch back on our boundary polyline, and then in this section, we can go to operations. A similar thing is to select inside visible polylines like we did on the point clouds. Selected inside those. I'll do operations. Delete selected. And there's a little bit of tidying up that we would need to do. Very quickly, you do that in edit. You can do polygon select. And then in there, we could also do the same thing. Delete selected, still one in there. I won't bother tidying that up, but you would do if you are working on your data properly. And then I can switch my Whitby data set back on. And we end up with a very nice tie between our digital outcrop data and the topographic data. So if you've got some good high resolution satellite imagery, so if you've got world view or something like that with really high resolution data, you can get quite a nice tie between your outcrop models and extending your models further using satellite imagery. Right. A good point to save. That's georeferencing data, merging different data sets and integrating your outcrop model with digital elevation data. Let's look at a few of the basic interpretation and annotation tools now. The most important thing you need to do when you're working with geological data like this, if you're doing presentations or things to go in reports, is we need to have a scale. We have a virtual scale bar, which you can put on any point in the model. Oops, let's see, virtual scale and put one in there. Yeah, so there we are. Any of these scale bars, you select them, the properties come up here. We can do things like change their color, change the height, the width, number of segments, can show labels on them. So that label isn't showing at the moment. We can change them to be a horizontal, or if we want to have triaxial, if you switch off horizontal, you get a proper triaxial bar, scale bar. If you switch on horizontal and the triaxial is on as well, you just get the two axes. And then if you're working with a triaxial bar or a horizontal bar like this, you can also change the direction that the bar is oriented. So that gives you a very good way of being able to sort of put decent scales onto your models. Some of the other tools that we can work with is we have waypoints, which we've already seen that you can just put into your data. Waypoints are a great way of just adding in markers. But any waypoint that you add in, you can just do a go to. So easy way of navigating around your data. And we have billboards. So I'll just find some billboard data. And billboards are just images. Let's go to let me just find where the correct place is. So it's an area around in here, and you can just about pick out in the outcrop model here that we've got some cross bedding in this section. There's a bit more detail in that cross bedding that we can drop in. So I'll drop in a image. And there's our image been put in there. There's a scale bar. You can see the same section here. You can just about identify the geometry of this outcrop here is the same there. And when we zoom in closely, see in detail that we've got overturning of these cross beds. It's possibly flow drag. And then also we've got some iron stainings, these Liesegang rings that are evidence of there being fluid flow through these rocks. If we want to move the position of our billboard, we have our in interpretations here, we can use our translation tool. Let me do it. Ah, there you go. That's it. That one. They 3D translate. So I can then move this around. And if you click on the different planes, you can move it in different planes. You click on the bars and just move along one axis. If you use Control and use the mouse wheel, you can change the size of the widget to make it easier to deal with. So a very simple way of being able to put your objects into the correct place once you've drag and drop them into the 3D view. We also have our measure tool, which allows us to just make simple measurements. And any of these, you select the measurement, appear in here, and it gives you what the true vertical thickness, and if you attach an orientation to it, it will give you a corrected value as well. So that's vertical measurements. We go to, also we can switch to making horizontal or 3D, which is a straight line distance in 3D. So you can make multiple different kinds of measurements. Labels, just simple values that you can add in there. They appear in the data tab. And another good way of just adding annotations into your models. Right. Those are the basic annotation tools that we've got. Just switch off that from being active because it keeps switching back to the active menu. Right. Let's look at some of the interpretation tools. The polyline tool can be used to digitize simple polylines. So the first mode is make individual clicks along a particular surface and double click to finish. If we zoom in on that, we're able to see the polyline vertices and the line that joins the vertices together. If we head over to interpretations and select the polyline group, we can change the way it's displayed. So we can switch the vertices or the nodes on and off. We can change the size of the nodes, and we can switch off the 3D trace, which is the line that joins the nodes up. We can change the size of the 3D trace as well if we want. To edit the polyline, we head over to Move Vertices. Simply click on a vertex when it's visible and you can drag it to wherever you want it. In this mode, when you drag, the vertex will always be attached to the outcrop model. You can do Ctrl-Z to undo the edit. The 3D Translate option also works on the vertices. And again, we have the widget where we can move the vertex out of the outcrop if we needed. And again, Ctrl-Z will undo the edits that you've made. There are some other digitizing options. We use digitized points to start with. We have draw mode. In this mode, you can just simply hold your mouse button down and drag along the outcrop. And again, double click to finish, and you see in this case we have a lot more vertices. If you want to reduce the number of vertices that are digitized in draw mode, you can do it by modifying this minimum digitizer spacing. So if I make this up to, say, 1 meter and use the same approach, draw, And see now, even though I'm moving along and holding the mouse button down, it's putting a vertex in about every meter on the outcrop. Double click to finish, and there are vertices. Click on a polyline to get its properties. You can add a stratigraphy and a comment in there if you need to. In the display options, we can also switch on and off planes. The planes will be oriented into whatever orientation the best fit plane is for the polyline, or you can go in there and say we decide we don't want to dip on that one, we just want it to be horizontal. You can modify it manually. We can also, with the draw on, just switch some things off here. We can also do things like create geopolygons. Let's find a good place to do this. So around here might be a good place. So a geopolygon allows you to generate a body around an object. Now this is a multi-story channel system, so we can build 3D objects that encapsulate a particular body. And we have some different display styles on this as well. Let's go to interpretations, and it is in geopolygon. At the moment, it's showing as a 3D body. I can switch off, show as volume, and we can then go to opacity here and change it to say 0.5. And we're able to have a colored body drawn on the outcrop. Again, we can show the construction data, and we can go to our move vertices option, and we can edit these and move these into different positions as we see fit, if we want to go in and edit our outcrop data. Sometimes you will find that your geobody or your geopolygon doesn't generate its geometry very well, and you sometimes get gaps appear in it. That's usually if there's a complicated outcrop geometry that you're dealing with. To fix that, you can add these things in called key pillars, which explain to VRGS how the geopolygon should be joined together and should be, the mesh should be created from it. And we select that and select 2 points. You see it puts a line between the two, and it says, basically uses that to help define the geometry of the geopolygon. So if you get some funny geometries in your geopolygons when you draw them, try adding in key pillars. You usually add them in where you've got a change in direction or a distinct change in geometry. Let's have a quick look at dip azimuth tools. So making structural measurements. Again, a variety of different ways that we can do that. So there's 3 points. We'll generate a structural measurement. I've just seen, sorry, I missed a couple of messages. Somebody's just asked, can I calculate area or volumes from the geopolygons? Any geopolygon that you generate has a whole set of statistics associated with it. So in the properties of the geopolygon, you'll see we have things like the extrusion direction, which is to do with the way it's displayed, the structural dip, which is your regional dip, your structural dip, which you need to correct for, and then our statistics. So we have the area, which is just the area of the triangles that make up the geopolygon, and that's got a complicated shape to it. So then you have a cross-sectional area, which is sort of corrected If those polygons, those triangles are on a flat plane, the area is slightly less. And it does that cross-sectional area perpendicular to the orientation of the geopolygon. Then we have the corrected width, height, and depth. So that's the corrected bounding box around the geopolygon, corrected for the structural measurements. And then we have the maximum thickness. That's done by going through each of the vertices in turn and projecting the one vertices from, say, from the top down to the bottom, and then that one from the bottom down to the top, looking for the intersection points, working out what all the thicknesses are, gives you the maximum thickness of that geopolygon, the average, and also your standard deviation. So you get an idea of how much it's varying. So something's gone wrong on the average thickness variation there, because obviously it shouldn't be negative. Then we can also add in to our geopolygons are the orientations, the paleocurrents. So we can do a add paleocurrent. We need to set a paleocurrent type. So let's just say it was ripple cross lamination, a paleocurrent direction. And then we say, okay. It's appeared in here. There's our paleocurrent direction. Once we've added them, we can edit them in here. Modal is whether you know that that is towards 178. If modal is on, you know it's a particular direction. If the modal is off, it could be either of direction across 180 degrees. And then we have our corrected statistics for the geopolygon, for the width and the thickness. So the thickness is corrected to the structural dip, but the width will be corrected to the paleocurrent direction. You can add multiple paleocurrent directions into the geopolygon, because when we do our corrected width and thicknesses, so we might want to do this if you're working, pulling out geostatistics, if you're doing a geocellular model, so stochastic modeling. You might want to do a corrected channel width thickness data set. Of course, the paleocurrents you find in a geobody like that, when you're in the field, they can be quite variable. They can be very variable. What we have done in the past is, rather than just choose one direction, we will do a corrected width for every paleocurrent measurement that we've got within that geobody, if there are multiple ones. And that will give you a probability distribution for your widths, rather than just saying it's a single width. You've got then get a range of possible widths. So you start to take into account the uncertainty that you have in your field data. Anyway, so that was our going back to geopolygons and adding paleocurrent information to it. We were briefly looking at dip azimuth data. We had added in 3 points. So I'll just do that again. Simply click 1, 2, 3. 3 points is all you need to form a triangle. If you've got a triangle, you can calculate the orientation. That's what it does here. Select any of them. It will give you your orientation information and some error information if you can generate it. Can't always generate any error information. It depends on which type of interpretations you're using. The accuracy of these is really dependent on the geometry that you're measuring from. If you try and measure data points and you click 3 points and they're in a straight line, so if they're collinear, you can't get a good measurement out of it, because the orientation can be anything around that line. So you need to be going around a corner. The closer you can get to an equilateral triangle, the better. That's not always possible. Even with, not much of a variation on the line, you can still get a good result, but always double check, go and look at it, look down, your orientation, make sure it matches with your expectation as well. So do a visual check when you're doing your interpretations. Sometimes, let's switch these off. So if we've got an area like here, where we can see quite a big area of exposed joint plane or fracture plane, we might want to use the endpoints approach, where we can, instead of just selecting 3 points, we can digitize multiple points around the outcrop. And it will calculate an orientation from those and attach it to one of the vertices. I can then go back in here and do the show vertices. And there we've got a record of the points that's always stored. So whenever you create any kind of object, all the vertices that you use to create it are stored. And the reason why we might want to do that is that there is useful information held within that vertex list. So we could, work out what the size of that particular exposed plane is. We can also use a 1 point, and that's quite useful when we're working with field data. We can just add in a field measurement. If we know where it is, we can click it on it and we can add in a field measurement. So there's a dip of 0, 0 that I've just added in. Right. Okay, so that is our basic interpretation tools. What we'll do now is, we've been going for about an hour, so I suggest we have a 10-minute break. I'll come back at past. If you've got any questions, drop them in the messages now. I'll review any that I've missed while I've been speaking and answer them just when we get back. So let's reconvene at past, and I'll answer any questions, but we'll look at some more structural related stuff. So using attributes, being able to extract structural information from those, plotting things on stereo nets, and I'll show you how to generate scan lines. All right, so short break, and I'll see you in 10 minutes. Thank you. Okay, everyone, let's get back to it. Right, let's have a look at using attributes as a way of helping you do your doing your interpretations. When you're working with outcrop data, we're normally working on a view like this, where we're looking at the RGB photorealistic version of the outcrop. There's a lot of information within the geometry of the outcrop that we can use to help get more from the data set. And one of those approaches is to use attributes. So I'm just going to switch on leave the outcrop model on alone. There we go. So I've switched off the elevation data, so we'll just have this data set running. It is in attributes. So there's a whole range of different attributes that we can generate for different purposes, but the one that you will use mostly is the tensor analysis. Now, the way that the tensor analysis works is that you define the size of a search sphere. It will go through every vertex that there is in your mesh. So your mesh is made up of a bunch of vertices that are linked together as triangles, which are then textured. So it will go through all of the vertices in turn and find all of the surrounding vertices that are within this search radius. And then it does an analysis on all of those vertices that are inside that sphere and comes up with a set of parameters for it. So it will go through every vertex in turn and do that. We'll tell it to generate attributes for dip direction or azimuth, coplanarity. Let's add collinearity, so that's how straight the points are. And then from the advanced attributes, we can use, say, sphericity or change of curvature. A lot of these are things that you might use in various kinds of statistical and machine learning based classifications. But for us as geologists, geoscientists, these basic attributes, particularly the dip, azimuth, the coplanarity, are the ones that we use the most. The rest of it can just be left as it is, and we click OK. While that's running, the mesh switches off. That's because it's actually doing some processing on the mesh. It doesn't want you to be making any changes to it while it's doing the processing. It'll take a minute or two for that to run. VRGS does use multi-processing, parallel processing on all of these, so you quite often find your computer goes flat out when you're doing various processing stages. So if my Zoom link is going a bit slow, that's probably why. Obviously, the bigger the mesh, the longer this takes, the bigger the search radius, the longer it takes. This isn't too bad. Sometimes you just need to let it run and go and get a cup of tea. Right, there we go. Our mesh has turned yellow. The notification bar here has turned yellow to tell us that something has changed and a save is needed. But we open it up and now we have our set of attributes. I'm just going to press save. And then we can look at our different attributes. So there's our attribute for dip. If we select our charts tab over here, we get the histogram of the attribute. So you can relate the colors in the chart here to what you see on the outcrop. So yellows are steep dips and the dark purples and blacks are shallow dips. Then we have azimuth, so directions. And again, so remember that this, because it's azimuth, that these values over here are actually right next to these because we're going from 0 through to up to 360 and then back to 0 again. This is showing we've got 2 peaks of higher value numbers of orientations in particular directions. Then we have coplanarity. So coplanarity is how flat the surface is. This is a fairly typical distribution that you get when we first run your coplanarity. So you get a normal distribution, but a lot of very high values with not very many, the value count is very low. So remember, this is a histogram. The histogram panel here, the red line on the left and the yellow line on the right are filters. So we can click on those and drag them. And as I drag them, you'll see that your color map updates. And we can start to highlight areas of high coplanarity. Now that's very useful for us because if coplanarity is high, it means that surface is very, very flat. There's a publication from this by Fernandez. I can't remember the year of it. I will find it and send it in an email after we've done this. But it explains how this process is done. So he comes up with some recommendations on what values you can use as a good coplanarity value. What, values above, I think it's about 4.5 are very good high coplanar surfaces, which you can get decent measurements from. I'm just going to, on this though, because we've got a lot of high values, I'm in here going to go to transforms and clamp to filter. And that will clamp the high values on that filtered data set. And now when I look at it, it's clamped them to there, and we've got much more of a spread on our distribution. Very easy way of being able to pull out nice flat areas on your outcrop. Now we also, of course, have our dip and our azimuth data. If we've got the dip and the azimuth attributes selected or created on a mesh, we can just show coplanarity. And I'm going to just bring my filter. So I'm only going to look at, or I'll do it the other way. Let's bring it down this way. So we highlight areas of high coplanarity, so very flat areas. And we could, with a little bit of care, make an assumption that a lot of these highly coplanar areas are perhaps fracture planes or joint planes. If we've got the dip and the azimuth attribute, we can also generate our structural measurements using attributes. So if I click on a point here, it will find the dip and the azimuth from that mesh's attributes and create an orientation measurement based on it. So therefore, we can quite quickly go into our interpretations and generate a set of measurements. Now, obviously, you would spend a lot more time making sure you got the correct values in there and you were doing the correct thing. On our charts tab here, we can also bring up a stereo net. Now, there are a couple of different ways of showing stereo nets in VRGS, but this one is this display in the stereo net here, when it's in the charts tab, is tied to what is displayed in the 3D view. So as I go and add in new measurements from the 3D view, so I'll add one from there, you see it automatically appears on the stereo net. That means that as you're building up your interpretation, your fracture interpretations on your 3D view, you see it generated and building up in real time on the stereo net. It allows you to do some, keep an eye on what is happening with your data. And there's also things that we can do in here. We can switch on the minor lines, change the way it's displayed. We can do contours based on the poles to the stereo nets. And then we can do a thing called correct regional. If you've got a regional dip in your data, so doesn't really apply very well in this data set, but let's try and do one anyway. Let's assume, say that this surface here was our regional dip. We could go into our dip azimuth. We're going to use 3 points. We show our orientation there. And then in here, I can do set as, and set this as the regional dip. That will also appear in our project properties. It's in one of the properties somewhere. Can't remember where I've put it. for the moment, but it's in one of the project properties and you can change it in there when you need to. Anyway, so we can go back to our charts view, and then we can say correct regional, and it will take the regional dip out of the data of your StereoNet and plot your StereoNet in a corrected orientation. So that's quite a useful thing when you're working in complex areas where you've got a lot of folding and you want to take out a regional dip and look at how things were before it was that regional dip was imposed. The other way you can get to a StereoNet is to go through the home ribbon bar here, and there's also in the Windows section we have StereoNet window. Now the difference between the StereoNet window and the StereoNet panel and the charts panel is that this works independently of what's in the 3D view. If I go to my 3D view, you see that we've got our orientation switching on here. If I switch to my StereoNet window, there's nothing displayed. I can display different things in this StereoNet window to what's in the 3D view. Whereas this StereoNet chart is always tied to what's going on in your 3D view. So they have slightly different functionalities. This is sort of really for real-time viewing what's going on with your data. And then this is when we're trying to do some more complicated analysis. So we can even do things on this as look at include orientation data from the point clouds and from the meshes. And that's something that I'd go into in the future workshop on structural mapping and doing structural analysis with VRGS. Right, another thing that you might want to do when you're working with structural data like this is you might want to generate a scan line. So a scan line is something that you do when you're doing fracture analysis, and you make measurements of fractures that you can see on an outcrop. You draw a line on the outcrop and you go along that line and you make measurements of the orientations, and then you can do things like work out what the fracture spacing is and various other parameters like that. Obviously, we'd need some really need better fracture data to do that properly, but the process is pretty straightforward. So we'll put in, maybe let's try and add in a couple of extra fractures in here. So I shall add in interpretations. I'm going to just use the same. I'm going to use 3 points. Put one there. Put one there. So we've got a set of fractures going along here. I'm going to switch off a few of the others. So we've got 3 fractures going along there. We have the tool in here, which is the fracture scan line. And this is a polyline tool. So we draw our trace along the outcrop, double click to finish. And it's in here. We probably need to change some of the display options on this. And what we should find is that we do have, where it's intersected a fracture, we will get information on. It links it together, works out where we've got intersecting fractures with that fracture trace, and gives you the information about the name of the scan line, what the set spacing is, normal set spacing, the P10 value, variability value, mean dip, mean azimuth. So that's a way of generating a simple scan line. You need to have gone through and done your fracture interpretation a lot more in detail than we've done here. And when you draw the fracture trace, it will only pick up the fractures that it intersects inside the triangle that the fracture, that the points have made. So that's something you just have to be a little bit wary of when you're using this approach, because sometimes, like this one here, it's missed that fracture because the polyline didn't actually go through the fracture that we'd interpreted. Just missed the outside of it. So you generate your fracture scan lines in that way. Right, so some other things that we can do. Let's just see if we've got... Oh, so okay, some few questions here. Is there a 3D stereo-net plot functionality? No, there isn't. There used to be. There used to be a version of the stereo-net that you plotted in 3D and had in the corner, which didn't get much use. So it kind of got commented out of the code quite a few years ago, but it's, you know, the code to do it is still there, to generate a 3D plot. It's one of those things that if there is need for it, it can be added back in. So I will bear it in mind, but I always thought it was quite a nice thing to have, but it didn't actually get much use. Right, so in this example, what would be the tolerable range of discrepancies between planes orientation model and actual on-site measurements? Yeah, okay. So for example, man measures using compass, we get dip angle of 15 for 180, but in the model we get slightly difference between 18 and 20 degrees. I would say, I mean, if that's the dip, if you're looking at a difference between 10 to 20 and 45, I would say that is unacceptable. I would expect them to be pretty similar. If you've got a real discrepancy, it's either because your polyline that you've made the measurement with is too linear, so you've got a high error on it. You could also look at whether your georeferencing is correct. If you're trying to georeference, say, with drone data, and you're just using the GPS points from the drone, they're not actually that accurate, so you can get some discrepancy there. I quite often, when I collect data, I put something like a 1 meter ruler into somewhere on the surface, or a long straight stick of some type that I can physically see in the photographs, and you'd be able to see in the model, and take an orientation on it, so like a plunge measurement, and you can compare that with what you get in your model to give you an extra check that your georeferencing is correct. So that's quite a useful sort of approach. It only works when you're working with fairly small models, but it's a good one to do. But I would say that would be too much of an error, and you need to look at why. So check that your polyline measurements, your orientations, are not too linear, that you are going around a corner. Sometimes you can find that your outcrop measurements are, your digital model measurements are better than you can get in the field. There was an example I had working in the Gulf of Suez where it was really difficult to get any kind of measurement in the field because it was a quite badly weathered calcarenite. It was really fractured and really, you know, no sort of, everything was really broken. But with the digital models, you could actually make measurements from bedding planes that you could see over the scale of several meters. So rather than taking a measurement on the scale of a compass clino, that you can measure on the outcrop. You've taken the measurement over several meters, and you were able to get better estimates of orientation that way. So it really does depend on your data. How can we draw sedimentary logs? Okay, let's talk sedimentary logs for the last section, all right? Now, right, okay, so sedimentary logs. Let's switch off these. Let's go to our data, and we're gonna switch off our coplanarity measurement. Sedimentary logging tool is up here, create log. Very simple to start with. You go up your outcrop and you digitize points where you have your bed boundaries the same way that you would do when you're in the field. So you make the same decisions about where you put your boundaries. Something I didn't mention when I was talking about the polyline interpretation is that if you're in the middle of digitizing and you need to move your model, just hold down the shift key and it pauses the digitizing mode, whichever digitizing mode you're in, and just lets you go back to move. So now here I'm in the middle of digitizing this, this log, but I'm holding down the shift key and I can move the model around. Release the shift key and we go back to digitizing and double click to finish. So there's our sedimentary log put in place. And to start with, there's nothing in the log, so I've double clicked on it and it's become active. So I'll do an add track. I'll add grain size in this one. For any of these, we can add a grain size. Now the grain sizes are found in the collections tab. And you can, so these are the default grain sizes that you're familiar with from, normal sedimentary logging. If you're working in carbonates, what's being developed at the moment is, rather than having a distinct group like this, we're switching to using these things called generic classes. And you'll be able to create a whole range of different generic classes, and we use for carbonates, we do them in a generic class. But anyway, so that's a sort of developmental thing. We can also in here add an image track. And to any of these, we go add image. And I think in billboards, do I have anything I can use in there? I'm just going to use the strat column. I don't have an image, log image that I can use. So in here, we put the start and the stop. So I'm going to put this stopping at 10. And it appears in the log like that. So this is where you integrate your field-based sedimentary logs, do a scan of your notebook, tidy up the margins of it, make it, clean it all up, get it so you can link them together nicely, and then you can import them all in here. Now there is a way that we can do, or used to work. No, it's not. I've switched it off. So usually there was a way that we could do an overlay image and put the image log underneath the grain size log, but I've not got that in there at the moment. It's something that I'll add back in. Anyway, so now we can go into our 3D model and see our image log, or at least visualized next to where your outcrop is. So that's one of the basic ways of doing it. If I remember rightly, there is a way of doing that as a projective image. I think we should be able to do this, but a long time since I've tried this. Let's see if it works. So let me switch off the log. Where I'll put it, there's my log. And there, now it's a little bit odd here because we're on quite a complicated outcrop geometry, but there is our image projected onto the outcrop. You can get some very odd things happening when you've got complicated outcrop geometries and it's going in and out like this. And there's a few things that you can do to change the settings on them. But that's the basics of how to do it. There are other ways of adding in your projective textures when you do it through make active, which gives you a bit more control. Is that there is an add texture here that you can do. That's yeah. Have we got any more questions? Or can we customize a color scheme for the attributes? Yes, we can indeed. Right, attributes. Let's look at the coplanarity, for example. Right, coplanarity, we have in our properties. Let me just modify the filter on this again. Right, so I'll go back so it's showing the full color scale. And right, so we have our coplanarity attribute. The properties are in here. We can change this color map from, we've got some standard color maps. Right, so we've got the 4 standard color maps: magma, viridis, inferno, and plasma. These are our standard perceptually uniform color maps. You'll know that, probably know there's this thing about we shouldn't be using the rainbow color map anymore because some parts of the color map are you perceive them stronger than others. So it's not a good way of displaying data. These color maps here, they're perceptually uniform. So the colors don't overly emphasize a particular part of the color scale, right? So that's good. Then there's a couple of elevation color maps which come by default, which are the VRGS and the Ordnance Survey ones. But we can generate our own color scales, and we find those over in the Collections tab. Down at the bottom, color maps. And you see our current default color maps are already in there. I'm just going to go new, and we can generate a new color amp here. Going from, let's do a nice green through to gray for the sake of it, right? And there's color amp 6, and there is our color amp shown in the properties, right? And you can actually go and edit the color amp values individually if you want to. You probably don't want to on something where you've got this number of levels, but we can go back to our coplanarity attributes, and we can now switch on our new color map, red, green to gray color map. Here's our chart. Let's pull down the scale bar again. And there we go. We've got our color map displayed. So I think something's got a bit wrong. Oh, there we go. Needed to update on the color scale. There we are. Yeah, so you can generate your own color maps. Color maps are also quite useful. How long we've got left? A few minutes left. Right, I'll share while we're on the subject of color maps. Now, you can also there is this website, which you can, I can put a link out to it, but it has a lot of different color maps that you can download and use. So they have a couple of data formats that they use for their color maps, which VRGS will import. So you can bring in a color map from those. The other time when color maps are really useful is when you're doing fasces maps. So there's several different ways we can do fasces maps. I've got this mesh is currently active. We can create a fasces map in here. And I've got to do show overlay. There we go, hold on. And right, we need to define any fasces. We select it. And I can do a paint. And I should then be able to, in my fasces here, just highlight that and filter out the null value, the 0 value. And then you can generate and build up an interpretation. It should actually not switch off the color display. So you can build up a fasces interpretation based on your fasces that you've got in here. So we might want to then go into our mesh. We can generate another fasces. And then we could put the fasces in there. Let me show the overlay. No, it's not showing the overlay correctly. But anyway, there's our second color map. We go into our collections tab and we have the fasces in here. We can create a color map from the fasces interpretations because each of these in their properties have a color associated with them. And then you can actually use that color map and edit it when you're displaying the fasces parameter. So if we wanted to go to our fasces map and display it like this, we can set our fasces color map in here. And then we should be able to do some filtering on it. So it's a good way of being able to generate fasces maps and attach them to your outcrop data. So it's not quite displaying correctly at the moment. But the way that I would use this is that I take these parameters into Petrel. You can extract your fasces map from your mesh as a point cloud with fasces parameters, take it into Petrel, upscale it, and use it as conditioning for your reservoir model. Right, so let's see. Okay, so we've done custom color maps. Have you ever thought of creating a Petrel plugin? Yes, I have thought about it. There are challenges with using Petrel to display the textured meshes. We've tried it in the past and the performance just isn't good enough to be able to handle these kinds of data. I mean, Petrel is a really fantastic piece of software. It's really good at what it does, but it's not really designed for working with digital outcrop data. I think is really what it comes down to. So we have a good export from VRGS into Petrel. There's some standard formats that allow you to get your data in very quickly, so you can do the integration that way. Can we generate a property map such as permeability or porosity? Not at the moment. In future, that is definitely something that is on the plan to do. And we started that with being able to put in, if you go into the interpretations, there are sample points that can go in. And you can add in these sample points, and the sample points can have a whole variety of different attributes attached to them. Just find me where I've put them. So there they are, they're in the data. A lot of the objects that we have also, you'll notice there's a subgroup inside the folder, which is attributes. And you can add a whole range of different attributes that are attached to a particular parameter. So here we could add a continuous value, which could be porosity. And then when you select your sample, it has that attribute, that porosity as one of its attributes, which you can then start to add to. So the idea is that where this was used and when we started developing it was somebody had a set of data that they collected in the field, they had X, Y, Z value, they had a set of attributes, and we were able to bring them in as sample points. And then they did sequential Gaussian simulations and Kriging in another package to generate a map from that. The obvious step is to take that and integrate that into VRGS. But again, it's something that's going to come in the future as we build up different aspects of the modeling. Oh, okay. Good question is about what is the best method to display the 3D interpreted model other than taking a screenshot. One way is to generate a movie and use a movie. And that is done using these things called flight paths. So I've just created a flight path in here, make it active. We get the flight path menu, just really quickly create a flight path for you, add view, and add a view. So we've got 3 viewpoints added into this flight path. From that, I can then say, I want this flight path, I'm going to set a duration and I want it to last 20 seconds. So the movie that it generates will last 20 seconds. I'm going to just quickly change this to different interpolation method. And then I'm going to do create open path. And now you can see the cameras, old style cameras, they represent your viewpoints. And then all of these arrows in between are the different frames that are going to be in the movie. We then take the flight path, we can do record movie. Let's just stick it on the desktop. Save. We have to set some parameters here. I'm going to save this as an HD movie. And in flight path, I'll press play. And this is playing the flight path. It's making a recording of it. That's got to the end. I'll stop the movie. Let's quickly see if I find where I've put it. It should be on the desktop. And there we go. So that's recorded a movie. That you can then incorporate into, put it on YouTube, put it in a presentation. It's great for that. The other way that you can do it is in the edit menu. There is a Sketchfab upload. And you do that, you would have to, you log into Sketchfab. And we're running out of time, so I won't go through the process here, but you log into Sketchfab, put in your, obviously, username and password, and then you get available from the same menu, from that edit menu in here, you get the upload scene. And you can upload not just your model, but the polylines and the scale bars will also go as well. So it pretty much, not everything at the moment, but the basic interpretations, if they're displayed on the screen, when you do upload, they get uploaded into Sketchfab as well. So you can upload a model with some scale bars and some polylines. So that's another good way of sharing your data with other people.